Hey there, everyone. My name is Ryan Schul. Welcome to my channel. So in the project today, I want to take a look at how we can stop identity fraud using feature engineering and anomaly detection. So this is going to be very interesting. I hope you can stick through the video until the end. We're going to look at some really cool, really fascinating stuff. So let's take a look at what is identity fraud. So one good example would be creating fake accounts on Facebook, maybe fake accounts right here on YouTube, um, creating all kinds of fake email accounts, right? And then spamming people with fake email accounts, right? So there's lots and lots and lots of ways that you can create identity fraud, right? And disrupt things a lot, right? It can be a big problem. So fraud patterns are basically hidden in raw data, but we can tease these out. We can sort of like flush them out, and there's a few different ways to do that. So I'm going to show you how, and we're going to jump right into it. Basically, feature engineering takes features that exist right now, and we create new features to make the data set more enriched or more refined, perhaps, or maybe the feature isn't really going to help us very much, like a date. Usually date features aren't helpful unless you're doing some type of time series analysis, then yeah, then it's critical. But a lot of times date features, the date itself isn't useful, but if you take out the year, the month, the day, is it a weekend, is it a weekday, is it a holiday, things like this, it can add a lot of value to the data, right? So that's just one example of feature engineering. It's creating new features from existing features. So fraud is usually rare, so it's kind of hard to detect these things, and it's easy for machine learning models to miss these fraud events because they're relatively rare. So most of the time, you don't see fraud, right? Most credit card transactions are totally legit, and the bank wants to permit those transactions to go through, right? It wants to stop the fraudulent transactions, right? But there's so few of them, sometimes they're hard to detect and to show the model, because the model has to learn based on a lot of information. But if there's only a few fraud transactions, it's going to be difficult for the model to learn what's really fraud, because it's only seen fraud a handful of times, right? So there's inherent challenges when we're dealing with these types of things. But again, it's very important. It's imperative to try to understand this and to detect this fraud, right, before it becomes a real problem. So especially detecting new fraud for the first time ever, we don't have any examples of brand new fraud, right? We have to determine, is this even fraud? Is it defined as fraud? If it is, then we have to train the model on a brand new type of something that we've never even seen before, right? So these scammers are very cunning, very tactical, and the process is constantly evolving and changing all the time, right? So what else? Scalability and automation is important, right, when we're doing these types of things. I'm going to show you that in just a minute. And basically, with feature engineering, we can amplify different signals that we can use to train the models and determine if activity is suspicious or not suspicious. We're going to use some anomaly detection techniques to listen for the signals and look for some kind of noise, or look for some kind of some type of pattern in the data that's highly unusual from all of the other patterns in the data, right? That's going to be defined as fraud. And using these techniques together concurrently, we can determine, what's a rare event, what's a fraud event, how is this fraud evolving over time? If it's brand new fraud, how can we try to learn that new fraud and prevent it from happening? So I don't have an actual fraud set. I'm going to create a synthetic fraud set that should represent pretty accurately what fraud would look like if it existed here, right? Okay, so we have emails, registration date, last activity, IP address, device, transaction amount, email domain, account, age, activity gap, and disposable email, false or not false. Okay, so that's the data set. That's what we're starting with, right? So we already have the features that look like dates, registration can be turned into time-based risk feature. IP addresses can be geolocated or analyzed for suspicious activity. Devices can be checked for sudden changes in device type, right? If you have an IP address that is unique, if the device, if the IP address was previously an Android and now it's an iPhone, that would be highly suspicious. Like how could that actually happen, right? IP addresses are unique, It's not going to switch from one device type to another. So things like email domains, something that's disposable or looks suspicious, that is something that we want to check for. Transaction amounts, right? Detecting high transaction amounts. I don't think fraud is going to be committed for 50 cents or for 75 cents, right? But if somebody wants to steal money, they're probably going to steal big, right? So a fraud transaction would probably be hundreds of thousands of dollars. It's not going to be little tiny transactions, right? Although if you had a whole bunch of transactions that were under a certain threshold, that could be suspicious too, right? So, for instance, a bank could look at every single transaction that exceeds $10,000. So, money coming into the bank or money going out of the bank, because it's not de minimis, it's a large amount, and the bank could say, we have to check this. This is a lot of money leaving the bank. We have to see what's going on, right? But if somebody's committing fraud, they could try to deposit or withdraw $9,990, right? So you're under that threshold, so the bank isn't necessarily looking at those records. But if it's repeat activity over and over and over and over, that can be considered fraud easily, right? It's under the threshold, so it's not really being examined with the same lens as those net transactions are, and net worth transactions are, right? But repeated activity over and over can definitely be fraud, right? So those are things that we have to look for as well. So I have other things in my notes here. You can take a look at this. I'm not going to go through every one, but frequent changes, right? Transaction amounts compared to past averages, something like that. Single IP linked to multiple accounts. So I mentioned that, right? We alluded to that one. Sudden bursts of activity after long inactivity, disposable or uncommon email providers, things like that, right? That could be considered suspicious as well. So it looks like my screen just crashed. Let me refresh this thing. I'll use this opportunity for a water break. Okay, so we've got a foundation here and lots of good stuff to get started with. So let me see, it's refresh. Okay, everything's back to normal. So this is what I was going to talk about before. We're going to create some new features from the existing features. So I'm going to create a brand new column in the data frame, right? I'm going to append it to the same data frame. Is high value TXN transaction, right? This is transaction amount greater than the average transaction amount plus 2 times the standard deviation of the transaction amount, right? So big transactions that exceed the mean and two standard deviations from the mean, that could be a high transaction account, right? And we can look for amount z-score, transaction amount minus the average transaction amount divided by the standard deviation of the transaction amount, okay? So let me go ahead and run this. It might sound like a lot. It's not that complicated. These are just bigger transactions, and these are transactions that exceed a certain threshold, okay? So hopefully that makes sense. If not, by all means, Google it. Check it out, right? Z-score, Google that. So that is, let's see, is high value transactions. So this is one new feature that we just created, and this is going to be a flag. This is yes or no. That's it. And then transaction greater than z-score. So again, z-score, we're looking for something that's an outlier, something that's bigger or smaller than the average transactions, right? Convert Boolean to int. So disposable email is high value transaction. So I think it just refreshes. Let me just do it again to make sure. Okay, so we have the new features now. So now we're going to go ahead and jump right into it using 3 different anomaly detection methodologies. Okay, so we have an isolation forest, an SVM, and an autoencoder. I'm going to take you through each one. We're going to compare and contrast the differences, and it's going to be pretty exciting, guys. Okay, so we will have to scale the data. Okay, I have something in my notes that explains why. We just want everything on the same relative basis. That's why we standardize it. So the standardization is called over here. So I'm calling it, and then I'm fitting everything that is an X variable into the standard scalar. All the x variables are numeric columns. So anything that comes up as a NumPy number. So what's a numeric column? It should be pretty obvious. That is not, that is not, that is not, that is not. This is numeric, okay? That. So those are going to be pulled in for analysis. And we can't do standardization on a date. That doesn't make any sense, right? We can't do standardization on an email address. We're looking at numbers only. So anything in these buckets over here is numeric, and that is what we're going to go ahead and standardize, right? And apply the isolation forest technique on this. So we have 1,000 records, right? Is anomaly false? 950. Is anomaly true? We have 50. So we have 50 of these down here. I'm going to go ahead and plot this right here, and we're going to see what the results look like. So anything that, let's see, anything that is blue is not anomaly. Anything that's red is anomaly. So false, blue, true is set to red. The data comes from here. This is the data frame, account age in days, and Y is going to be the transaction amount. Okay, so we're looking at account age. Is it a newer account? Is it an older account? If the account has been around for years and years, and it's pretty normal, it's probably legit, right? If it's a brand new account that was created 15 minutes ago, and the transaction amount that we're looking at here is pretty huge, right? Let's say $50,000, $100,000, and you just created the account, that can be considered an anomaly, right? So that could be fraud. That could be considered fraud. And the color is coming from here is anomaly, right? So that's the first example using isolation forest. Most of these are not anomalies. Some are. And when you put the mouse over the bubble, you can see all the details right here, right? So anything that is anomaly, we should probably do an investigation or at least try to understand, like, why is this being flagged, right? So here's the next example, SVM, slightly different technique, but same type of anomaly detection goal here, right? So the goal is essentially the same. False 498, true 52. Over here we had 950 and 50. Okay, and when I plot it, we'll see the plot looks like this. Control Enter. And here's the plot. And honestly, guys, this might be a little bit intimidating. It might look like it's kind of a lot. Could look kind of confusing, but it really isn't, okay? You have to just look closely at what's going on here. Do some research on Plotly. When I first started looking at it, yeah, I was confused too. It's a lot to take in all at once. But, you know, if you do this a few times, it really becomes much more second nature and much easier to deal with. So the data comes from the data frame. The X is one of the columns in the data frame, right? Count, age, and days. So Y is the transaction amount. The color is SVM anomaly. So this is the new feature that we just created and appended to this data frame, right? And this is anything that says SVM anomaly equals 1. And the concept is very similar over here. We're using a different technique. This is isolation forest. Anything that is anomaly equals anomaly score 1 is appended to this new feature, which is new column in the data frame. This is a data frame, and it's just a different anomaly detection system that we're using here. So this is isolation forest. This is SVM, okay? And it comes from this library over here. So all the stuff comes from scikit-learn. They give you this stuff for free, right? You just have to do a little research, a little investigation to see how this works. All I did over here was change the color to yellow. So if it's an anomaly, it's yellow. The blue stays the same. I'm doing the same thing down here. So I'm importing this. This is autoencoder. So autoencoder comes from here. If I do Control F, you can see where it's coming from, right? So all these autoencoders are still scaled just like the other two. Whenever you're dealing with some type of clustering or some type of anomaly detection, you're always scaling the data. I've got in my notes a couple of reasons why we want to do this here. We have false 970 non-anomalies, 30 anomalies, right? So let me go ahead and run this. This is autoencoder, so it's actually doing deep learning. So this is more like a human would learn, right? Traditional classical machine learning is not deep learning. It's pretty straightforward. It's all statistical based. These deep learning models use inputs, a transfer layer, or a layer where everything is analyzed, and then the outputs. So it's really a whole different kind of level of thinking. It's supposed to represent how a human mind thinks, or how a brain would process information. So it's actually pretty complex because you have all these inputs, all these outputs, but what happens in the gray matter in your brain in between? Scientists have researched this for as long as I don't know, going back probably decades, maybe even centuries, and nobody really understands the human mind, right? But there's a lot of amazing stuff that goes on inside your brain to process all this information. So somehow the inputs are created to outputs, right? But exactly how is that actually done in the brain? We don't know. For these autoencoders and these deep learning, TensorFlow, what else? PyTorch is a big one. Haras is another in that bucket. Um, it's pretty complex. It's pretty convoluted how these things work. We'll just leave it like that. So in this case, we have 989 non-anomalies and 11 anomalies. Again, the only thing I'm changing over here is setting this true to orange. And again, this comes from autoencoder anomaly. If the mean square error is greater than threshold, create a new feature or a new column in the data frame, append it to the same data frame. So the data is the same, X is the same, Y is the same. We're mapping false is blue, true is orange. When I plot it, you get a slightly different plot from the other two. Now there's fewer anomalies, and these are kind of congregated down here in the corner. All right, so there's a handful of those. What did we say it was? 11. So these are kind of spread out a little bit more, but you can see it's on the fringe. It's kind of on the edge. So the SVM is performing a little bit similar to the isolation forest, where you'll have sort of like anomalies in the different quadrants, right? Like northwest, southwest, southeast, northeast. Kind of the same representation over here. With this autoencoder, it's kind of different, right? Everything is sort of congregated in the southwest area over here. So so that's it. So why are we actually scaling all of these? For the isolation forest, it's not strictly enforced, but it does help the computer to process information a little bit faster, and it doesn't create a whole lot of bias. So it's just easier for this model, this type of learning model, to just learn the information and create more accurate predictions. For the SVM, it really is critical because the SVMs are all distance-based. Anything that's a support vector is distance-based. So large-scale features are going to distort the boundaries of this SVM sort of environment, right? And it's really going to produce some weird results if you don't standardize the data, right? So it's just very good practice to always do that with any of these anomaly detection systems and any kind of clustering technique that you do. It's also highly encouraged to standardize the data. Autoencoders, same thing. Neural networks train faster, so you get the output quicker, and it takes less processing power for the computer, right? So you're burning less energy, less heat generated by the system, and you just get the result faster, right? So that's win-win-win. That's what you want. So why don't we compare these three techniques and just see how they work? I have a lot of stuff in my notes. I don't want to like spoon feed this to everybody and force it on you. You can read the notes, but basically the isolation forest tends to be pretty fast. The strengths are working well on large data sets, works well on tabular data. I would say in this case, probably the isolation forest might be the best one to go with, right? Of these three, this one might be the best just for these reasons. When you look at SVM, it learns for normal boundaries and future space, and anything that's outside the boundaries are considered anomaly. It's good for complex decision boundaries. We really don't have this. We have straightforward tabular data, so rows and columns. So the data set isn't like this three-dimensional amalgamation of data points, right? It's pretty structured. It's pretty straightforward. So I would say the SVM might not be the best one to go with in this case. And weaknesses, scaling is critical. We just saw that, and sensitive to hyperparameters, right? And slower for large data sets. So it's another reason SVM, well, this data set was only 1,000, so we can't even say that in this case. Small to medium, and you suspect anomalies are non-linearly separable. So this is not really the case here. If the anomalies were not linearly separable, right? From the normal points. This is a great model to use because it can detect this weird patterns in the data, right? But we don't really have that here. So I don't think this is necessarily the best option. I would still go with isolation forest. Autoencoders, basically, again, these are neural networks trained on normal data. Anomalies are reconstructed from poor to high reconstruction error. Strengths, very flexible, can model nonlinear high dimensional patterns. So that's great. I don't think we really have that here. And is this time series data? It actually is. So this could be one argument to go with this. Weaknesses needs more and more data. This is a deep learning neural network. So we only have 1,000 records here. That's not a lot, right? If you had millions or hundreds of millions, this would probably be a better choice. Sensitive to architecture, training quality, scaling is essential when you have enough data to train a neural network. Again, we have 1,000 records. That's not much. So probably the isolation forest would be the best choice here. So in the last cell here, I have the final results of everything. This was the original data that we looked at up into disposable email, right? Then we started to create some new features over here. This is high value accounts and the Z-scores. Then we got the anomaly score, and this comes from the random forest is anomaly, SVM anomaly, and autoencoder anomaly, right? So based on these three models, remember I said we created a new feature, which is basically a column, and appended this to the existing data frame. So that's how these get in here. That is the head by default. That is the first 5 records. These are the last 5 records. And again, this is what we did to the data. I guess like we actually started here. So it's this high value. These are the Z-scores, anomaly score. And then that's random forest, SVM, and autoencoder. Okay, so that is pretty much most of it. I wanted to look at one thing right here where this comes from. Oh yes. So that actually came from isolation forest, right? So there's the data frame. This is the new column, or the new column that we appended. Anomaly score. This comes from isofit after we scale the data. If anomaly score equals 1, then we say is anomaly, right? So actually the isolation forest created this and this, and SVM and AE created their own separate columns all by themselves, right? So the the isolation forest, did it in 2 steps, right? Whereas the other two, the SVM and the autoencoder, did everything in 1 step, right? So here's the first step for isolation forest is anomaly. Based on that, we create another new column, right? So those are the 2 steps there. And that's the plot. And then from SVM, we have SVM predict, SVM anomaly, SVM anomaly. So everything is done in 1 step. There's the plot. And then for isolation forest, if the mean square error is greater than threshold, then we create this new column in the data frame and assign the definition anomaly or not anomaly. Okay, so that's it, guys. That's a lot of stuff. Okay, finish under 30 minutes. That is good. I'm trying to become a little bit more efficient when I'm making my videos. I don't want to drag on. I want it to be entertaining, informative, enlightening, right? I don't want to drag this out for 45 or 50 minutes. I did have some long running videos. I had a couple that went over an hour, but that's pretty rare. I'm trying to get these down a little bit in time to under 30 minutes. If I can communicate the message in under half an hour, that's great. I think that's wonderful. That's going to be my goal going forward. Unless some of these are just going to be long running by nature, I think, but there shouldn't be too many, right? So my goal would be try to get everything done in 30 minutes or less. And we're definitely under here, right? So under 25 minutes. So I think we're coming out ahead. So that's it, guys. I'm going to wrap it up right here. Thanks for your time and attention today. Always appreciate that. Thanks for sticking with it to the end. I am going to wrap it up here. I'm going to download my file right here, my code, and share that with you guys. So you have all the code. You can copy, paste it, run it in your own Jupyter Notebook environment, and you'll have everything that you need, okay? Anything that you want to change, by all means, you can change it, okay? Any of the inputs, the way you do the analysis. If you want to test a couple different other anomaly detection techniques, by all means, go for it. Use Google, use ChatGPT. If you don't understand something, research it, dig in. You're going to learn a ton. I promise you, right? And if you kind of know this stuff, hopefully this is filling in any knowledge gaps that you might have. And if you're an expert with this stuff, um, then that's fine too. If you're at a mature stage in your career where you know this stuff like back of the hand, that's fantastic. Then congratulations for that. Okay, so I'm going to wrap it up. Thank you again for the time. I'm going to end it here, and I will see you in the next video. Goodbye.